This video is going to cover measures of agreement and reliability. So just to start with, there's some definitions. Reliability is basically the ability for a test to get the same result or a similar result if you repeat it. And this is kind of an umbrella term that encompasses some of the other terms that I'm going to mention. So repeatability is the ability of a test to get the same results when repeated on the same subject under the same conditions. Reproducibility is kind of related. It's the ability of the test to get similar results on other people or maybe the same person in another setting. And agreement is just the extent to which two tests come to the same conclusion. And that's very analogous to sensitivity and specificity, which was covered in another video. So it's important to assess agreement for a variety of reasons. If you have multiple people collecting data through interviews or just through various processes that have some subjectivity involved, it might be useful to calculate how often they're coming to the same conclusion on the same subjects, which ideally they should have perfect agreement if your goal isn't to measure agreement basically, but if your goal is to just have uniform data collection, it's important to see if there's systematic differences in how people are collecting data. You can also compare your measurement with the gold standard. This is useful when say there's like a very slow and expensive way to measure something, and you want to do it for like 10,000 people, so you're gonna for pretty much everyone you're gonna measure this using like the cheap version, but you could take a subset of them, like 100, and measure them both using the cheap version and the very time-consuming and expensive version. And if you find that there's pretty high agreement in the results between your rapid test and the gold standard test, then that adds a lot of validity to your results. There's also certain designs like matching and case crossover that rely heavily on concepts of agreement and disagreement between paired observations, basically. So some measures I'm going to talk about are percent agreement, percent positive agreement, Kappa statistics, and I'm not going to talk about sensitivity and specificity, but they're a related concept, basically. So let's just say we have this data, and these are two observers looking at the same data. So basically, each person in the yes cell is someone, like let's just say it's diagnosing disease. For someone to end up in this cell, then both interviewers had to come to the conclusion that the person has the disease. Similarly, if person 2 said they have the disease and person 1 said they don't, they end up in this cell, and vice versa. If person 1 thinks they have the disease but person 2 doesn't, they end up in this cell. And when they agree that the person doesn't, they are in this cell. So these are called concordant cells, and that's when the two people agree, so the yes and the no cells. Discordant cells are usually the information-rich cells with respect to like match design and paired design. So basically I highlighted these two cells because they're what is most important for the calculation of percent agreement. So I have a video on measures of frequency that covers like what a proportion is based on like a 2x2 table like this. But it's basically the sum of the concordant cells, so the sum of the agreeing cells here, the green ones, over everyone in the study, basically. So 10 plus 12 over everyone, it comes out to 0.71, so a percent agreement of about 71%. There's some problems with percent agreement. The main one is that it's influenced by the prevalence of the thing we're looking for. So if it's really uncommon, then this negative cell is going to be high just due to chance alone, rather than by nature of there being high agreement. And it doesn't take into account agreement due to chance. The idea of agreement due to chance is something that you might be more familiar with if you've ever calculated a chi-squared statistic, where basically you're able to figure out the expected value in each cell that would occur even if people were just choosing at random. If the event is really rare or common, the chance of agreement is higher, or the chance agreement is higher, basically, and this can make it look like agreement's stronger than it is. Percent positive agreement is something that helps account for this in the sense that it helps take into consideration how common or rare the event is. So if we have our same data as before, you find the percent positive agreement. This formula boils down to something more palatable, but just take a look at that for a second. But it ultimately gets rearranged to this, which is a little more palatable. So percent positive agreement, it's 2A, so whatever's in this cell, the agreement cell, and B and C. So basically it's the amount that are positive for both the yes cell over pretty much all the agreements, so the amount that are positive for both and the amount that are positive for one. So C is only positive for this person, and B is only positive for this person. So yeah, using the data that I had before, we can do 2 times 10 over 2 times 10 plus 5 plus 4. And you get a percent agreement of 69%, which is a little bit lower, and that's because it took into consideration the possibility of agreement by chance. Kappa really takes into account the agreement by chance, and it even has like a testable hypothesis that has like universal interpretations. I'm not sure if that's true. Kappa is typically calculated by hand, but I'm pretty sure there might be an associated hypothesis test with like a p-value. So yeah, basically it accounts for the idea that even if both people, like I had person 1 and person 2, are just choosing at random, there's still bound to be some agreement due to chance. And Kappa basically figures out how, like, taking into consideration how much agreement due to chance there is, which is a function of how common the event is. It's basically figuring out how much the observed agreement exceeds that. So it's the observed non-chance agreement over the maximum non-chance agreement, basically. And this is what the Kappa statistic works with. So the proportion of observed agreement minus the proportion of expected agreement over 1 minus the proportion of expected agreement, which is the same as just, I believe, just the same as the maximum non-chance agreement. Yeah. So PO, the observed proportion, is something that we've already calculated for this data, because it's pretty much the same as the percent agree. Yeah, it's pretty much the same as the percent agreement without multiplying by 100. So you have 10 plus 12 over everything, and 0.71. For finding the chance agreement, it's a little weird. So first I'm just going to show you these. What I did here is it's like yes, no, yes, no. I've added a total column on both sides. So like I added 10 and 5, 4 and 12, 10 and 4, 5 and 12, and adding all of them comes to 31. Because they're what's involved in calculating chance agreement. So each of these cells has an expected value due to chance, and I'm just going to remove them because they're irrelevant. They would all change if because these are the observed distribution. We can figure out the expected distribution just using this information, basically. So I'm going to refer to these cells as A, B, C, and D. And the expected value for cell A here is the marginal total for basically. There's two marginal. This is called a marginal total. It's in the margin, and it's a total of its respective row. So like this is a total of this row. This is a total of this row. This is a total of this column. This is a total of this column. So A is defined by a column and a row, 15 and 14. So basically, to find the expected value for cell A, you multiply its total of the column it's a part of, the total of the row it's a part of, 15. And the total of the column it's a part of, 14, and then divide by the grand total of 31. So you end up with an expected value of 6.8. And for we do the same thing for D, and we basically only care about these cells because we're trying to find chance agreement. So chance disagreement is something we could find, but it's irrelevant to what we're doing right now. So the expected value for D, if you just do the same thing, we do the sum of the row it's a part of, the product of the row it's a part of, 16, and the column it's a part of, 17, and divide by the grand total, and we get an expected value of 8.8. So now we can figure out the proportion of expected agreement, the same way we found the proportion of observed agreement. So basically we figure out the observed agreement. This 31 is going to stay the same because the number of people has stayed number of people will stay the same, but we've just redistributed where they are in the table. So we figured we add up the chance agreements, yes, yes, and the chance agreements, no, no. So 6.8 plus 8.8 divided by the grand total, it comes out to around 0.5. So now we have everything we need to calculate kappa. We have the observed proportion of agreement, the expected proportion of agreement. So we can plug all that in and find a kappa of 0.42. So what we learned from this is that this kappa is much lower than what we were calculating before, like 0.71, and that's because basically there's a high probability of chance agreement with the way our data was structured. And as far as interpreting a kappa value, I get this is multiplied by 10. Basically, I should have just had it it's 0.2, 0.4, 0.6, 0.8, and 1. Kappa goes from 0 to 1. I don't feel like going back and changing this, so I guess for all of you listening with sound, which I think is probably anyone who's listening, just know that this is supposed to be 0.2, 0.4, 0.6, 0.8, and 1. So I guess like what we got was 0.4 something, 0.42, and that's fair, pretty low. But like moderate agreement is like 7, and anything above 8 is considered very good agreement. Weighted kappa is something I'm not going to do, but I'm just going to briefly explain what it is. So before we had like a dichotomous thing, like yes, no, but let's just say there's like a spectrum, like going from like very high all the way to like neutral, low, and very low. Disagreement might not be weighted evenly. Like for example, someone who said like if this person said high and the other person said neutral, that's like more similar than if this person said very high and the other person said very low. Where like very high and very low are a greater degree of disagreement than say like low and neutral. So yeah, weighted kappa is basically calculating a kappa statistic where the cell, like the cells, basically what is considered disagreement and agreement has a different weighting, rather than before where we were weighting it all equally. And sensitivity and specificity is relevant to this conversation, but is covered pretty extensively in one of my other videos.